Okay, so we are recording right now. So we're going to be talking about the Matlab toolbox over here. And what I have is a collection of notes I have not posted of what I would like to talk about. Essentially, what I would like for you to look at when you create your own, when you write your own Matlab code. Most likely you are going to end up writing this code for your project, right? Or to confirm your own code. So, and I spend a lot of time looking at what are the issues. Can we get the light off? We're going to have a little fun today. It's going to be about Matlab. So, believe it or not, the biggest problem in coming up with this lecture was to alter the material so that it does not become a cheap version. We're not going to do a tutorial on Matlab. We're going to show you what it does so that you can go inside and learn this material as you need it, okay? Because, so the first one, I'm going to put this online. It's going to be called the Optimization Guide.pdf. It comes from, this is the best document to start you up on how to decide which software to use. And basically, I have some notes. The first thing to realize, of course, I'm only presenting the material that I agree with. So I agree with pages 1 and 2. So you need to decide what type of objective function you have. Linear, like linear programming that we're covering right now. Quadratic, like sequential quadratic programming, often used in support vector regression and other things, right? Sum of squares, least squares. This is a huge, huge subject that the more I looked into it, the more I realized how little you are exposed to. So I'm going to go a little bit more in it today. Smooth, but non-linear. When we say that a function is smooth, yet non-linear, that means that smooth means you can evaluate derivatives. You can take Hessians, okay? And then the last one is non-smooth. This is when we started looking into problems such as simulated annealing, right? Completely nasty. In fact, we put, if you remember in the homework assignment, you actually had a nice function, a continuous function, but it was not sampled at the regular positions. It was sampled at the integers, and it was not defined. Your function was not supposed to be defined except at the integers. So it looked nasty, right? It looked noisy, but it wasn't, So non-smooth could be anything, okay? All right. So you guys understand, this is the first, they're right. I agree with them. Again, I'm only presenting the pieces that I agree with, okay? The second thing is, and this is very important, is to understand the kind of bounds you're going to be working with. They have a little bit about the screen, but essentially nothing. I mean, don't even think about Matlab. They aren't constrained. Simple bounds, they're talking about lower bounds, upper bounds, like numbers, 4 and 5. They're not talking about functions. Okay? Linear constraints are treated differently than non-linear but smooth. Let me explain. So linear means like matrix type, AX equals B, AX less, like what we did for linear programming. Notice how I delayed this lecture until we covered a little bit more about constraint optimization. General smooth means that you can evaluate derivatives, and most importantly, you can evaluate gradients of the constraints. Okay? So very ugly, non-linear, yet smooth. Okay? Then the other part that and I have a little guide in front of me on my other screens looking at what I liked, okay, about what they were saying. Obviously, I'm not going to, this is for Matlab, but I'm only presenting the stuff that I like. So they have a very nice table in there that I agree with. Notice how they organize the linear, quadratic, least square, smooth and non-smooth, but besides, and then they go, what kind of constraints? So this first line over here is all unconstrained optimization, everything we've done before we got it. Then you have very simple bounds. Notice that linear programming, oops, sorry, Maybe I'll find my cursor right there. Linear programming is right here. It's a linear constraint with linear bounds. That's not only linear, they're constant over there. Okay? And then you can solve, by clicking on it, you'll find the function that you can go after. So you can have least squares with 4 and 5 type of bounds, and you will be right here. Okay? By the way, I have a much better recommendations for least squares. Again, linear programming. Now we're talking, instead of just constants, we're talking about AX equals B, AX less than a vector, linear bound. Okay? And general smooth, as we said, we're talking about being able to take derivatives. Okay? Smooth, you can take derivatives. And these are the functions that they recommend. It doesn't matter if these are the functions that they recommend or not. What I would like for you to understand is that this is a good starting point. And that's why I'm recording my lecture. The other thing I want to do is jump to, and they have the different methods. Jump to page 6. Okay. Unless I'm missing something, this is page 6. Wonderful presentation of, you can ignore Matlab, but it's a wonderful way to understand how the software has been organized. Exactly what we're doing, but notice that it's a basic optimization for scalar, meaning that x basically a homework number 1. But notice that in addition to homework number 1, they allow some bounds, which is essentially what we did in homework number 1. We had bounds everywhere. You guys put them there, right? So unconstrained optimization, I guess it requires no introduction. You know what I'm saying. The only thing I'm going to caution you, and I did not check this carefully, is that they might be using a slightly different notation than us. There might be a minus sign, okay, somewhere. I didn't check it, okay? You need to check it. My only feedback is that be careful because the inequalities might require a minus sign, okay? It's no big deal. Just do it. Put it inside A or B, okay? What is wonderful here is to understand is that basically in this linear, this is the general form that they can take without you having to make no effort needed on your part. If you have, again, the linear programming constraints, this is what we did last class. You have less than B, remember, bounded above, right? And then you have equality constraints, AX equals B, equality here. And then you have bounds on X and Y. By the way, we're going to talk a lot more about how to take full control of the toolbox. It's actually fascinating to me how they organize this toolbox. The great news for you is that they use exactly the same language as we use in our book. Interior point, I mean, there is nothing that you need extra to start running all this software. That was not, there is no language that we did not cover. Okay? So with this lecture, you should be able to go after them and handle any tough problem usually required in the toolbox. Remember, all of you can download this for free on your laptops. Quadratic programming, we did speak about this in the trust region methods. By the way, they do have trust region as well. They're talking about, in some sense, notice that there are constraints. So it's not the trust region. It's actually further down in the constraint optimization in your book. Simple quadratic, X enters the quadratic. Notice there is no constant. There is no int for it because when you're optimizing, the constants don't affect anything, right? And we have an equality constraint, linear, equality, and bounds. Exactly the same structure as above. Okay? Let's go after here. I just want you, again, I'm sorry to repeat it. I spent a lot of time figuring out how to present this, okay? I think this is the easiest way for you to step in and start using anything that Matlab offers and understand what it can do. The functions can change, but the problem and the notation, I think, is going to stay. All right, so constraint optimization, exactly what we're talking about. By the way, and I'm going to say this, and I'm going to say it again, there is K-nitro, which is actually the last chapter in your book, which is actually written by the authors of your book, and Matlab has an interface to it, and it's also open source, and that is probably that is the one that I would strongly recommend for running constraint optimizations, and I'm not sure, and I don't think it's fmin-con. Okay, so but let's look at these problems again. Non-linear. This is a non-linear, but the assumption here is that it's probably smooth. And as you shall see as we keep discussing how Matlab works, if you do have gradients, Matlab you can use them. So if you can differentiate this function, you can specify. And I'll talk about how you do that later. Okay? I'll talk a lot about the nice examples that I liked. Equality, inequality. Notice how they are always separated. Again, repeating myself. Equalities and inequalities. This is supposed to be nonlinear. If it's linear, you are not supposed to use this notation. If it's linear, you're supposed to use this. Okay? Because it will run faster. Okay. Lower and upper bounds, these are vectors, just like everywhere else. The semi-infinite is slightly different in the sense that I didn't really look at it very much. So I'm not going to go into it. Some of the variables can go to infinity. We haven't spoken about it, and this is really not much. I won't talk about it here. There isn't that much there. If you have this type of a problem, then my recommendation is to look at the global optimization toolbox, and so is theirs. They also recommend the same thing, using genetic algorithms. They have a global optimization, and I agree with that suggestion. That's what everybody says. And I'm not covering that today, maybe by the end. Okay, let me see. We're on page 6. I did want to talk a little bit about I did want to talk about the multi-objective, even though it's really not. We haven't spoken about it, so I'm sorry about that. This is a little bit ahead. This is interesting. Does anybody know about minimax? You basically, okay, so let's talk about it briefly. You plug in a value for x, and you look at the maximum error, and you're looking at it at different positions. So it's like, let's say you have so in multi-objective in this case, you have, let's say, 3 different functions, right? 1, 2, 3. And you might be measuring how far off you're getting with each value of x. You know what? I'm not covering it quickly, so I'm going to skip. I see the questions in your eyes. If you understand multi-objective, it's here. Forget it. I'm not going to focus on it. We can come back later. Okay. Some of the more basic solutions. These are equation solvers, okay? This is basically, think about this as homework number 1, problem number 1, but multiple dimensions. So what is new, there's actually nothing new. There's a whole chapter in your book. The only thing that is new is that instead of it's actually much easier than optimization. Instead of trying to minimize the gradient, take the whole gradient to 0, all you need to do is take the function to 0, okay? Usually, for example, what we're usually doing is trying to take the magnitude of the gradient to 0. So they're using Newton in multiple dimensions, exactly like your first assignment, but in multiple dimensions. And the first one is regular AX equals B equations. Notice equal number of variables. Then we have the nonlinear case. In this case, it's one variable like your homework, and then they have one for nonlinear. Now, this might sound innocent, but if you only have one constraint, nonlinear, you can go ahead and use this, right? Find the solution. Remember how we spoke about this? It won't work very well because remember how you need to figure out the null space and all that. But at least it will put you on the boundary. So this could be used to initialize you, right? So you could, if you don't know what you're doing, you have a very nasty problem, and you have all of these equation constraints. How do you even start? It's a nightmare, right? So if it's only one, or excuse me, n equations, n unknowns, n variables, you could probably use this function to start you up, to put you, to create a feasible point, a nice starting point. All right, I'm going to talk a lot about this part because it is by far the most fascinating. It's actually the most fascinating story about least squares was that I discovered that there is a much better story to tell, which I will tell you today. I hope. Yeah, our timing is good. Okay, so let's talk about least squares. Okay? So again, optimization over x, right? This is the regular ax equals b, even though it's cx equals d here, right? Regular least squares, and Matlab does it with just a backslash. Okay? Just type help that and you'll see it. Then there is non-negative least squares, where we have an extra constraint with that your function, all of the variables have to be positive. For example, pixels in an image, or there is a lot of physical quantities like speed or energy cannot be negative, right? Constrained least squares, similar ideas. Notice that in this case, all of the constraints are linear. Non-linear least squares. By the way, this formulation over here is very, very interesting because what is happening, this is one of the primary reasons for teaching this, is that notice that they look at the error in every coordinate. Do you understand what I'm saying? For example, if you are doing least squares fitting on a curve, you are basically looking at the error at every one coordinate, and as long as you fit the error for each one of them, Matlab will construct Hessians, Jacobians, whatever it needs. And that makes your life very easy. So we'll talk about this later. Again, what is fascinating is this equation right here, because it basically, as long as you can specify the error at every point, it will build all kinds of stuff for you. And then this is a far more what do I say? Let's just say it this way: a much more honest way of looking at it, and it has incredible implications. And I'll talk to you about it in a minute. Here you're saying what I'm really doing is I have some data x, and I have some points y, and I want you to tell me what happens, what do I plug in. I think about 1/3 of the class has this problem, okay? And you guys have this problem. And what happens to solve that problem is that we discuss this later. You remember how many different approaches can you take? I'm going to mention 3 of them. There are 3. One, you look at it as an optimization problem. 2, you look at it as a curve fitting. There's a whole toolbox. We're going to talk about that in about a minute. Not a minute, but hopefully today. And the third one, which is the most professional way of looking at it, look at it in terms of statistics. So this innocent little last thing has at least 3 different approaches, and to my big surprise, you can cover the most advanced function in 3 lines, and I'll talk about it hopefully before the end of today. So this is by far the most honest way of doing it, where you are fitting data in and out, and you're trying to form hypotheses, you're trying to see you're doing model fitting. It's much more honest than just of course they're using optimization to do it, but they have a very different philosophy of how to do it. So I really like these functions because that's what most of you have, right? Whether you're designing antennas, whether you're fitting real data, this is what you're doing, the last one. So my recommendation for all of you that are doing nonlinear least squares is to at least look at this formulation, okay? If you have real data, and I'll show you in a bit. Okay, and other than that, I'm done with this. I'm going to post all of this online. I mean, you can get that by typing help something, right? Okay. So, by the way, this is an example of extending least squares that I'll talk later today. It's actually the lasso and extend elastic nets, which I really, it would be nice if you can do your least squares this way, excuse me. All right, the other document that I want to put online is actually this one. Notice that so far, what I have done is talked about the theory, right? Here are the equations. Here is what we spoke about in class. Please make sure you understand there are linear, nonlinear constraints, and please understand that there are bounds, and those need to be treated differently. Now, you know, it's 2 weeks before the last week of the semester, and you need to give me a draft, and you want to run some software. Where do you start? Okay, that's the problem. That's the problem I was trying to answer. And I'll probably, depending on what I see from you, I'll post it tonight. I mean, they're all in Matlab. Okay, so what I wanted to do here is cover pages 1 through 4. And this is what I want you to see. There's a sea of information, and I wanted to organize it so that you can follow it. So they give you an example, and notice that here is a function here, x. Notice we have x1, x2, right? And notice that the inequalities could look this way or they could go that way, right? And one of the first, I guess the first thing they are doing is that they want to put them in this form. I think ours is greater than, right? Yeah, we like positive. So like they're using them, right? I think we have positive for us. Okay, I'm getting old. I used to. All right, so the first thing is they make the inequalities have exactly the same. Can you see it in the back? Okay, I'm recording it too. So, is to have exactly the same, right? And then they want to build, just like you did in your homeworks, they build an objective function which should correspond to this, e to the x times 4x1 squared plus 2x squared plus exactly what we put is 657. Save that function, nothing there. Okay? Then, and this is the interesting part, is you need to specify the nonlinear constraints. So there are two functions. By the way, the order matters, not the name. I'm pretty sure about that. In fact, I don't want to test that, but trust me on that. First one is the inequalities. Second one is the CE equalities. So EQ means that when you're talking equalities, then they need to go inside here. And notice that there's nothing there. That's how they say there is absolutely no equality constraints to consider. Nothing. Okay, very easy. Okay, here comes the x. Notice that the x is a vector, can be an arbitrary size vector, but it needs to be the same size as that one, right? That's the only thing you can screw up. Okay. So, you don't need to put the less or equal to 0. You just need to put, it doesn't matter how you organize it, right? Because it's going to get evaluated. Okay? And then the only thing you need to remember is to put a semicolon to go through your equations. Are we clear? Semicolon for each equation. Very easy. Now let's call it. Okay? So how do you call the function? Initial condition, x0. Okay, second, specify the algorithm. We're going to go into that a little bit, but right now they're using the active set. The concept of active set is basically, I mean, I have to look at what they're saying, but active sets, remember how we talked about active constraints? That means that they keep track of which ones are valid, which equations, which inequalities are active. That's what they're talking about. Which inequalities are active. That's the active set. And then they call the function. They pass the add. What do they have to pass first? Again, we're having fun. This is right before Thanksgiving. That's why we're taking it this with this. I always like I hate myself for doing this, but I hope it will save you some time. Name of the function with the add. By the way, the initial conditions, a bunch of other constraints we're not using, so the order matters. Be careful to count how many empties you have. And then the constraints, and then the options. But the options were set by Optim set. Okay? Run it. Outcome, it gets back the value. That's the error. And this is the minimal point. Just like your exam second problem. Is this correct? Is this a feasible point? So what did they do? They look at the nonlinear constraints. By the way, this one, it didn't have to be 0. But remember what I said earlier. The best solutions are on the boundary. So if you're running linear programming, it's not going to give you 0 on every constraint. It will give you 0 only on the constraints that are active, right? Okay, so it didn't have to be that all of them are 0. It happens that both of them were intersected at the right point. That didn't, and then of course there's nothing for equality. Okay. Okay, and there are many examples in that, but I guess I did my duty and covered one of them. The other thing that I want to talk about is adding gradients, which basically says, notice that in the example we have here, there are no gradients, there is no Hessian, there's nothing. Okay, so that's what happens when you want to add them, and I would like to talk about that on page 4. So you can read through the rest. I mean, they're not very different from what I covered, like using infinities and all that. There's nothing there. Okay, that's just unbounding it. Okay, this one though, I want to talk about step 1 and step 2, because okay, so how do they add all the gradients to make that a far more efficient optimization? Then again, it's a very simple idea. Let me talk about it with you. Let me ask you a question. Do you know what n-arc in and n-arc out refers to? No? Okay. N-arc in is the number of arguments that are in. N-arc out is the number of arguments that you are outputting. So let's work on this together. N-arc in for calling this function will be 1, even though x could be a matrix, because there's only one variable. So you can call it, remember Matlab has this, you can write a function here with like 20 different parameters on the left and 20 on the right, and you can call it with 3 on each side. So the way you write your function so that you can adjust according to how many cases they give you is by introducing the n-arg in and n-arg out. So basically, when you run this function, if you write 2 variables for the output, then n-arg out gets the value 2. Is it clear? Okay. If you only write 1, then this condition will fail, and you will not estimate the gradient. And by the way, unless I'm missing something, I am sure. This is also the way to specify the Hessian. So you just specify right here. And when you call it, you remember you're going to pass the function to the optimization toolbox, to your algorithm. If the algorithm is using gradients, it's going to call it with 2 parameters on the left, and it will call this function, and you're done. If the function is using Hessians, then you need an H. You need to define how the H is going to happen, right? So if you write it this way, the way they have it, then you can write one function that can be used with algorithms that use gradients with algorithms that don't use gradients. You understand what they're doing? One function for all of them. You can compare them if you want it. Otherwise, forget the ifs. Just do it once. So there's nothing there. Okay, there's nothing there. You just take the derivative and plug it in, okay? It's interesting. They don't need the dots anymore, huh? Put the comma. I wonder if it would work. I would put 3 dots here. All right. All right. Now, notice that the same thing happened here. They have the basic things we had before, but then they have the derivative of C, and then the derivative of C equals. This is wonderful. Remember, because the advanced nonlinear constraint optimization algorithms, they're not going to want to, Let me ask you a question. What do you think will happen if you don't pass these two functions? Based on what we did in class. What do you think they're going to do?
Estimate?
Yeah, how? Estimate, correct. How do you do the estimate? Numerical derivatives. What is that?
The difference in functions.
Finite differencing. Exactly like your exam number 3. Remember all the problems about that? If you don't get those points, finite differencing could really break down. You have to be very careful. Okay? So if you don't pass those two and they need them, they're gonna do something stupid. Or hopefully it might work. Finite differencing. So my advice is that if you have them, differentiate them. Use the symbolic toolbox. I have a whole example how to do that. By the way, I did the same example in Mathematica and I could do it in one line. They have like a bunch of functions. Mathematica, if you have it, it's wonderful. Okay, so there it is. The two C's, and then notice that they're in the same order, right? If I take a derivative of this constraint, how many variables do you guys see? 1, 2, right? So notice that, so the DC will be a vector function. That makes sense. Derivative with respect to x1. Okay, so that should be x2, right? This one gives me a 1, right? So that's the
It's the other way around.
no, this is the derivative with respect to x1. I guess they are doing, notice that okay, let's take it about it. I made a little mistake there. This is not a vector. This is a matrix. Okay? Let's work on it together to make sure that we understand how it works. The first row corresponds to the first constraint. So if I take the derivative with respect to x1, I get x2, and I get a minus 1. This goes away because I took the derivative with respect to x1. Right? Now if I take the derivative with respect to x2, it goes, I guess it went down. It's along the column. It's x1, x1, what else do I need? And the minus 1. So, conclusion, every column covers the gradient of each constraint. So now I got it right. So, column 1 is the gradient of C1 with respect to x1, respect to x2. If I'm right, I should be able to test it again on the second column. Let's do it together. Otherwise, I messed up. Let's try. If I take the derivative with respect to x1, right, then I get minus x2. That's correct. Let's go to the second one. If I take the derivative of the second guy with respect to x2, I get minus x1. So, it's correct. Every column corresponds to the gradient of each constraint. Are we clear? Notice that these are not equality constraints. These are the C's. These are nonlinear constraints which are less than or equal to 0. Unlike your book, which I believe is greater or equal to 0. Okay. So, all right. This is what I want to cover here. By the way, I spent a lot of time trying to come up with a lecture that makes sense. Believe it or not. I hope it makes sense to you. Okay, the next thing I want to talk about is go all the way down to page 6. That is a very interesting example. So here is everything I said. Here is how they call it. You can work through that. Here they tell you how to specify no, it's a similar idea that we did before, sorry. It's a little bit It's a little bit different. Okay. Somehow I liked to talk about specify Hessian using the Lagrange multiplier. Okay. So again, this comes from the theory that we just covered. So if you form a Lagrange multiplier, right? And notice that you have equality constraints and you have inequality constraints. So these would be inequality constraints versus the EQ. EQ means equality, and when there is nothing, it refers to inequality. Remember, they're using the less than or equal, 0. And these are the Lagrange multipliers that go with each constraint, right? And this is the Hessian. So what happens here, I found that interesting, they allow you to evaluate that. Remember, it was the last theorem on chapter 12. So how do you specify this? Let's see if we understand it. So the only thing that is surprising for me is how they pass the lambda. You see the lambda? Everything else is kind of standard. If you look at the example of what they were doing before, you'll find the same ideas that we had before. But the basic age, the only thing that I would like for you to notice in this example is lambda is a structure vector, a structure that has two types of multipliers. The inequality ones and in fact, in this case, they only have about the inequality ones. So that's all I want to say. Everything else is the standard. I mean, you read the problem, everything comes from the previous equations, the previous pages. So the only thing that is interesting and the only one I'm going to highlight in my lecture is this is how you pass the lambda. The other stuff is given above. All right. And I think I'm done. Oh, okay. Then I want to go all the way to page 12. I want to talk about something else that relates directly to your exam. Oh, by the way, they have this nice example of how you go through the menus. And then, right after they are done with that, they have, let's say you don't want to use the menus, how do you run it? Directly from the prompt. And they're equivalent. What I found interesting to talk about is page number 12. Are we here? 12. Okay, you see they have a very sparse Hessian. For example, in problems in image processing or in signal processing where you only look at a couple of pixels at a time, so it's completely sparse. Or most of your problems, you're doing differential equations in control theory, your problems are sparse, okay? Or you're doing differential equations in process design. They're a bunch of zeros. So if you are going to fit the Hessian, you would like to tell the Hessian where the non-zeros are, right? So my comment there is to go to line page 12. Are we there? Yeah, this is the equation. Look at this. You see this? So if you are, and I'm highlighting in my lecture, and you guys study more if you want to work on it. So if you are working with differential equations or you're working with sparse problems, then you would like to say that the Hessian pattern is specified by this HSTR. You can read and do more about how that is specified. But remember how I was placing ones on the non-zero entries. That's the only thing you need to say there. Where are the non-zero entries? And what it will do is theoretically, unless I'm missing something here, is to create, and you should be able to define that with HSTR, with sparse functions. What they should be doing is using that sparsity not to kill your computer. That's what I'm going to say. Okay? And also, in the problems that you're going to do for me, I don't think it will be a problem of memory. It's just a matter of efficiency. So if you can pass out the non-zero values, then hopefully it will run faster for you.
They've got a whole set of stuff out there. They've got a sparse matrix data structure.
Yeah, they unfortunately they have the SPI. The SPI shows you where the non-entry zero values are.
Yeah, that's assuming that you can represent your data using the sparse data structure.
You,
Sparse data structure, it'll store all the non-zero values.
that's right.
It's,
But they have a lot of support for it. This is, remember, this is it's not really MathWorks. This is like 1950s and 60s. That was incredible. That's done. So you have a sparse A, sparse AX equals B, and A is really sparse. Theoretically, you should be able to find every. I think it's a simple command. I don't know if it's
yeah,
here.
it's called sparse. You just
Yeah,
sparse.
sparse.
Sparse and put the vector or the matrix into the.
So if you call sparse, it will probably bring you back the structure to pass here.
Yeah.
What is happening here, though, is that this is if the Hessian is constant, like okay, constantly. No, it should not move. Okay. Anyway, read this example. I haven't played with it. I confess. However, the sparse thing is what keeps linear algebra in business, because otherwise you will want to write a function, right? Because it's wasted. You're wasting millions of entries for no purpose. So you absolutely do need to. Okay, the last thing I want to talk about, I'm going to put all of this online, is go to page 19. A lot of you did this in the homework, by the way. You use the Matlab symbolic toolbox to generate, it's right here, right? Page 19. Use the Matlab symbolic toolbox to generate everything, to verify that your solutions were good. I really like that. So this is you get it for free now, everybody downloads. Let's talk about it quickly. So what if you have these nasty problems, like the ones that I assigned to you with for loops and all, and you want to generate Hessians and gradients? They actually give you a really nice answer, and I appreciated that one. So let's talk about it a little bit here. They are talking about Xij. Actually, I'm kind of cheating. I'm not giving you the problem here. Cell array. What's important? What is interesting to me is notice how they generate the Xijs using strings, right? So basically, the symbolic, the message that I'm getting from them is that if you want to use the symbolic toolbox, you better know how to play with strings. Okay? And you are welcome to read that. Okay? And then they notice how once they created these strings, right? They put it in a 30 by 1 vector, so it's the standard notation that we use all the time. And they said they pass the X. Notice that this X over here is a bunch of strings. So they pass strings to sim. Yes?
I think this must be older MATLAB because you can now do a Sims X 10 by 10 and it'll automatically populate it with X1, X2, X3,
Okay.
all within it.
The sim command here is just simply identifying X as a symbolic element.
So this might be an older MATLAB, and you can specify with just one command. Okay.
Yeah, and it'll populate all of them.
Okay. So keep that in mind. I just what is interesting for me though is the interface between the toolbox and MATLAB itself. And basically, if you don't have to populate all of them, this will probably generate. I don't know. So thank you for the comment. But basically, what they did, and what's important for me right here is they specified it as real, valued, symbolic, and then anyway, yeah.
Because if you don't do that and you take a gradient, you'll get weird answers.
You know,
Because
they take a transpose.
it'll take a transpose.
So this might not work.
Oh,
No, it does as long as you assign it real.
Yeah. If you
The
don't-
real
Oh,
is
okay.
important.
Yeah.
So that was the thing that might get it to work, the real part. Okay. Anyway, I'm not going to go through it. The most fascinating piece I think about all of that is to notice this as well. This is a symbolic, right? Jacobian.
Yeah. You can do a numeric Jacobian too.
Yeah. But I guess the great thing about this is that it will take derivatives for you, right?
Yeah.
Okay.
It's an overloaded operator.
Okay. And I guess. Oh, and then the other thing that again, I'm not going to talk about this very much. The other thing that if you want to notice, they create a MATLAB function at the end. You know, I've done the same stuff over the summer where I wrote code to write code, and basically my feedback is, okay, if you know how to play with strings, you can do everything. That okay, don't worry about that. I'm not going to talk about it anymore. Only if you want to do it. And obviously, some of you are already doing this. So it would be nice if you guys are interested in automatic derivatives, play with that. I can tell you that I'm doing the same thing with Mathematica, and Mathematica is just a D command. It's amazing. One line. I'm not, one line. Nothing like posted it up. One line. Forget it. So if you have Mathematica, forget about Matlab. That's my feedback. Okay, the other thing that I wanted to talk about is the Optim set. Okay, because the documentation for Optim set. By the way, I might extend this discussion, but this is the basics right now. Okay, and I might let you go early if I'm done, but I doubt it. All right, so no, actually, my wife will be waiting with the car. You know what's going to happen. If we keep going beyond, whoops, this is recorded. If we go beyond like 3:20, the children will be out the door. Which I love them, but probably not a good way to, because they're waiting for me to go to leave. So, all right. So optimization set, and by the way, when we go to implicit filtering, which is like state of the art optimization, so they follow similar ideas. So here is the Optim set. Remember how the Optim set. Remember all the things that we were talking about in class. How do you set the initial Hessian? How do you set the algorithm? How do you set Optim set? It's a structure that communicates, and also, if you don't use Optim set, you can call it to figure out what it's doing. Okay? How do you set the maximum number of evaluations? How do you set the tolerances? How do you set? Basically, it allows you, it's not as nice as writing your code or open source code, but it gives you some control. Okay? And you can, and it gives you some control. For example, it allows you to compare iterations. I don't even know if it gives you, I don't think it gives you amount of time it took to execute. Okay, so first of all, notice that we have large scale problems, medium, both interior. So they classify that, and I don't know if they tell you what large means. But here are the options. I'm going to go over them very fast. Okay? But look at what you have. You can pick the solver, the algorithm. Here is the functions that will read that. You understand what's going on over here? This is the size of your problem, and these are the functions that will pay attention to what you're passing. In other words, all the other functions that are not listed here, they don't care about what you said. Okay? That's the way it works. Always honor constraints. Ooh. I guess I thought that was important, but sometimes you can get out. Okay? Branch strategy, derivative check. Interesting idea there. So basically, the idea there is if you can do this basic problem, I found that interesting. And you pass them a function that actually is supposed to be the gradient and the Hessian, and they run finite differences, they get to look at it, whatever. Diagnostics. Also very interesting, and I just hope you, I guess this is, it's very, this is not a lesson about CAN software, it's a lesson about how they design the CAN software, more than it is. Remember how, when you get too close, remember what is the worst thing that you can do on a computer? Does anybody remember? Do you guys remember that? The worst thing you can do is subtract. So how do you avoid that problem? You pull the numbers away. We had a lecture on that, how far away they need to be. Okay, it is beautiful theory that we did in class. So one way to control all the noise that happens when you take differences is by keeping the distance between the variables, right? I haven't used that. What I can tell you is that I failed to evaluate derivatives using finite differencing in my experiments, and maybe I should have played with this a little more, okay? All right. Similar idea. I have to look at what they mean. Minimum change. You have to play with them to figure out what they are doing in a very simple example. Unfortunately, now you are asked to basically mess with this to see what they are doing. You probably have to reinvent.
It's almost like they're asking you to give the Lipschitz criterion for your continuity.
Well, they're not going to do that. I think they might ask you for that later. They should.
Well, I'm saying those other two, basically those are the two terms that go into the Lipschitz. You look at the marriage
No. I don't think they're talking about the L, the Lipschitz constant that we cover in class. I don't think that's
what.
bad.
I'm saying you can use a constant and then derive what you need to put into those two based on that.
Oh, yeah. No, this is about numerical. This has more to do with the number of bits, I think. Not the Lipschitz. No, sorry. That's something else.
No, that's what I was asking.
That's something else. Okay. Detail. This is also interesting because it's something you guys understand, right? What type of finite differencing? Let's see. They have forward, which is the one I think we wrote yesterday on the exam. On Monday. And then the central, which goes left and right. So it's going to take more values, double, because they have to go to the left and the right. And it's a little bit more accurate, but you spend more. Okay. Check the valids. So, all right. Is there anything else we want to talk about? Okay. I guess you could, if you pass, notice this one, you could pass your gradients for nonlinear constraints. I guess we already looked at that. But they are also giving you the option to specify separately. I guess it only works for these three functions, which have nothing to do with, I guess, I'm not sure how they conflict with the previous example that we spoke about. Don't ask me, I don't know. I really don't know. Okay, and other than that, the most important things are, look at that. This is very important. We spoke about it because the sparsity. Because if you have very large problems, you really want to understand that because you don't want it to run slow. No surprise here. I'm just highlighting the ones that are interesting. The initial radius in the algorithm that you guys did on Monday. No surprises. Again, Jacobian pattern, large scale optimization, maximum number of evaluations, exactly like you have in your homework. Okay? Max iterations, which is different. There are some preconditioning. Again, a lot of max to make sure this thing doesn't go forever. Okay? All right. Well, did I want to say anything here? Let me see. Okay. I'm going to close this, and then I have what we call an example. So here it is. That one was a little bit of a top, like the theory behind setting things. And this is an example of how you set it up. Okay? So you go parameter encodes, the value, and so forth. And you can just type it, and I'm sure it will give you the current and defaults and whatever. Let's see. I guess if we go through here, there are some examples. Oops, maybe not many. Okay. There's some example of how to set the tolerance and number of iterations. I guess if you pass it like that, okay, never mind. You play with it. Enough. All right. The last example, before I let you go for Thanksgiving and have fun. The big thing that I would like to say in closing about OptimSet is that I think we mentioned the sparsity, we mentioned the trust region, we make sure the maximum number of function evaluations. There is one more option. which is very, very common nowadays. Do you guys know? What is the latest computing revolution that we're supposed to take all of the computing curricula to teach everybody how to do? Tell me? Regression? No, that's coming up, but that's not what it is.
Objects and classes.
Huh?
Objects and classes.
No, that's old.
GPU.
Parallelism. Excellent. Yeah, GPU. Parallelism. So I wanted to tell you that I guess I didn't see that. Maybe it should be here. You got it. Parallelism. GPU, basically. Yeah, it's the most. So somewhere in here, without much effort, I'm not sure if I can do it. Maybe I can find parallelism. So they have the large problems. Let's go down to P. Maybe we can find it, because that's the big thing that I wanted everybody to see. O, P. Somehow I saw it. How do you search it?
Apple F.
Okay, thank you. I think I'm glad I have another Macintosh user because I'm learning here. Okay, parallel. I'm learning the Mac. I love it, but I haven't used one in 20 years. Hey! It's under U. Use parallel. So theoretically, basically, if you have a GPU that it sees, it should use it. So obviously, since we are very interested in large problems, it's nice thing to tell you, right? Especially since you're up all night and you're trying to write my report for the next day. If it's parallel, maybe it will work faster. I'll make you fun, but the up all night is what I'm trying to avoid. You know what's bad about being up all night is not knowing what the hell is going on.
Yeah.
For years. Sometimes. Because nobody, you know what's funny is, as a graduate student, the most frustrating experience, and I don't know if you share it, is when you work on this and you go to your advisor, he just doesn't understand, or she, you know, they don't care, they don't understand, they just want the results. So they cannot really help you. All they are telling you is that you don't have results, come back tomorrow. Well, I'm hoping to address this a little bit with all these checks, okay? All right, so we're done for that part. Now, the other thing that I wanted to talk about for today, and then I'll let you go, I might let you go a little earlier, is it's okay, I always pay back, right? I mean, you guys don't feel like I'm cheating. I always work my hours, right? No? I just want to live with a bang, okay? So I want you to go enjoy Thanksgiving, because I still have to prepare another lecture of how to use all the other things I want to see. And this is the greatest thing I want to leave you with. So this is my turkey. No, this is dessert. This is not turkey, this is a pumpkin pie. Okay, this is the pumpkin pie.
Great cooking.
I remember how we talked to you about being at this conference, and I was like, oh my God, what is this conference? And they had an optimization session, and these are people I really respect and I love. I mean, I love them. I'll do anything for those guys. I mean, in one case, this guy I was using his book as a student to learn how to do things, right? And I realized very quickly that they really didn't talk about optimization very much. But the one thing that so I was taking notes, okay, how do I come back and give my students, so I'll give you one more hint. He was from Caltech, okay? I was like, so what does he tell them at Caltech when they have to do an optimization problem, okay? What does he tell them? I mean, obviously I know what I'm teaching, and he said lasso. I was like, oh, okay. Do we teach it? Of course not. So what's going on? We're not going to have a second class education at UNM. That I promise. I mean, this is the thing. I have a confession. My wife is in the College of Education, and there are some books that they require everybody to take. One of them is called The Pedagogy of the Oppressed. If you guys have time, it's a Brazilian guy who wrote it. You know him, Pablo? You really need to read it, okay? It's not that, and I read a little bit of it because I couldn't read it. I read as much as I could. The point is that, believe it or not, you could be teaching people. It's all about attitude. I don't think they're much better than us in every respect. I think they have some great people and sometimes they do some great research. But most of the time we overlap a lot, and a lot of the things that we do, they don't do. I'll give you one example. Matlab. It was done here. Okay? So it's enough, I think. I don't need another one. Okay, so they told them they were using Lasso. Oh, why are we not teaching Lasso? Because they're running this function. I'm almost certain. So what is Lasso? So one of the biggest problems, and this, by the way, Lasso is used at Stanford. In fact, it was a Stanford creation. It's not, when you see it, here is what it is. Actually, there is a generalization of Lasso. It's the elastic net. And so this was his recommendation instead of regression and all these other things. And so let's work on it together, okay? I'm going to go over every variable to explain what I'm doing here so that you guys might end up using it. Basically what it is let's work on it slowly. What are the y's? The y's are the response. Those are your measurements, right? What are the x's? Is the locations where you put. So imagine you're trying to do y equals ax, okay? Y equals, it's a regression problem. So what they are really solving is that at every location, at location xi, right, you multiply all of your x's. Let me explain. X1 by beta 1 plus x2 by beta 2 plus all the way xn times beta n. And then they have a constant. So they know what the x's are, and then they know what the y's are, and they're trying to feed that. Right? That's what they're doing. And they're doing, basically at every location, we have n points. 1 through n. How do you plug them in, right? First point, you get y1 minus beta 0 minus x1. Remember, x1 now it's a vector. I'm sorry, just make sure I don't confuse you with many components. Multiply it out. Okay. So this is your regular least squares. So if you guys, just like every class at UNM, will teach you how to do that, right? The P or the A, use the transpose and invert that, right? Okay, but then there is, let me tell you a little bit more about that because it's way advanced. Remember, this is the pumpkin pie. The problem with least squares, does anybody know what it is? Why do everybody uses it, but give me one reason why you shouldn't use it. Okay. There is a famous, let me just, it's okay. All I'm going to tell you is that this is a revolution, quote unquote, how to modify least squares to get it to work. What happens remember with least squares is that if you require, I'm not going to go through that theory, but I'm sure you've seen it in many other classes. If you require an unbiased estimator, then the least squares gives you the minimum variance. Now, what happens here is that you could get overfitting. In other words, if you let go, if you allow your estimator to be biased. Does everybody understand what I mean by biased? Okay, bias means on average, you don't get 0, like on the error, right? Right, DC gain, that's another way to look at it. But anyway, if you don't understand those things, the only thing to tell you is, if you guys are working with least squares and you're looking for something better, I strongly recommend you look here. Okay? So they have the second term, right, which modifies the solution, and there is a little lambda, which for us to understand how that enters, we need to talk a little bit about multi-objective optimization. Because notice that the lambda is not optimized for, they play with it. The other thing they play with, and this is the recent stuff, we're talking 2012. The other thing they're playing with is little alpha, and the alpha shows up over here, you see it? Okay. And beta. So do you remember what are the betas? Those are the coefficients, right? I have a little Matlab at the end. I'll show you. It's coming out of here. Those are the coefficients. Okay? Those are the coefficients. This is basically, the second term requires those coefficients to be sparse. Where is my compressive sensing guy? Yes, sir? He's not here. I think the person who will have mostly benefited from this pumpkin pie is not here. All right. All right. Okay, but it's okay. I think the rest of you. So this beta, what you want to do is put some constraints. One of the most interesting constraints on the beta is this one here, which basically tries to put the betas to be close to zero if possible. In other words, this is what they call about sparse sampling, the other theories that go with. Did I get the right name, or did I offend somebody who's here? Sorry, but the guy missing. I'm making fun of him, that's all. All right, because I was thinking of him when I was doing the lecture, yet it's not here. No more. All right, so basically notice that all these constraints is about the beta. That's what I'm going to tell you. The theory, in order for us to cover it, we need to hold a whole class on machine learning at Stanford, actually, which covers this in like 3 weeks. I'm not going to do it in 5 minutes before Thanksgiving. I'm just going to tell you how it's done. I'm just going to tell you where to go. Okay, so basically you want to minimize. So the theory behind that is when you plug in alpha equals 1, you get lasso, and when you change it, you get different solutions. And let's see. Okay. Okay. So lasso is basically what they call regularized least squares. And essentially what it does is that it sacrifices the bias. It's considered to be state of the art. It gives you a least square solution because you saw the quadratic term in there. But then what it tries to do is gives you a better estimate of what you're fitting. And you can set up other parameters in the equation that I have described, vector. Okay, I'm just going to go quickly at it. And then out comes the different predictor. Okay, so the basic lasso for alpha equals 1, I guess in that case, notice that not the elastic net, the one that I was describing was a more general case. This is a special case of it. Only requires that you have the regular least squares, and the second time you just add the absolute values of the coefficients. So let me ask you a question. How do you make this? How do you minimize this alone? It's obvious.
You make it as small as possible.
You make them.
It's a summation, right?
Right. So you make the betas go to 0, right? The optimal solution, if this goes alone, is to make all of them 0. Okay? Clear? Okay. So basically, think about it this way. If you're doing let's say we're doing AX equals B, right? And we have 0.00001 multiplying X, then, that one will probably get replaced by 0. On the other hand, if you have like a very large number, like 10 to the 20th multiplying a function, that one will really get this very upset. It will try to find a smaller number to fit your data. Okay? So it will drive the guys that are closer to 0 towards 0, and it will drive the infinite ones to more reasonable bounds. Okay. So the example they show, which I have over here, and that will be the last thing before I let you go. By the way, I'm going to post the PDFs. Is right here. So what I've done is I have 100 by 5 random variables. Now, the reason I'm using 5 is because I want to be able to do X times R to generate the Y's. So let me say that again so you guys understand. These are the coefficients that I'm plugging in. You see this? I'm putting a 0 on purpose Remember, this elastic net likes to take small values to 0 and try to see if we can estimate it. Then I'm putting a 2, 0, so I have 1, 2, 3, 4, 5 in a column vector. And then x times r, what it does, it takes the random points, 100, random points, and multiplies them. So if you were to see the size of x, it's going to be 100 by 5, 100 observations with 5 x's inside, getting multiplied to generate the y's. So we are also adding some noise, right? So this is noise. This is data, okay? This first random is actually data. It's where you are making your measurements, okay? And the second one is noise. This is real noise, right? So it's signal plus noise, and then you run the lasso. In this case, interestingly enough, it created 46 different fittings, each one of them they're basically trying to estimate 2 and minus 3. And you can see that it went pretty good. Okay. I wonder, can I, yeah. So the lesson of this is, obviously there are more of this, which when I went into it, remember they come from the machine learning community. So what they are doing there is that they're extremely interested in the variation of what is happening. You see that? So they generate all these different samples, different fittings, so you can actually create confidence intervals. So this is pretty advanced stuff, right? I mean, I'm not going to go in. All I'm trying to tell you is this lasso command, if you are interested, I guess this is what they were using at Caltech. It's not a big deal. But it's a really alternative way to use something more reasonable than least squares. Having said that, I think my last message will be, and I guess I'll wait for that next time, is that this is the living thought, is that if you have problems like that, then you have basically regression packages, analysis of variance, and other options that should be looked at pretty seriously if you have the time. What happens, knowing you, I mean, people do PhD dissertations on those things, is you just want to run it and get out. And so lasso might be a good answer to that if you are not interested in a full-scale analysis, right? Okay, so have a great Thanksgiving, and thanks for coming, and I'll